Swayam Prabha. Digital India. Educated India.
This lecture is largely about where things are going in the American standard for the 2027 specification. Talked about this a little bit during the lecture last Thursday night. Some minor improvements to the first sections of Chapter F, which addresses flexure, but those are largely remaining the same. And there's going to be an attempt to address non-prismatic members and provide guidance in the specs to make it clearer how we can use elastic buckling analysis for design. So some of that is showing up in sections F1 and F2. But the major change in the 2027 specification cycle is to take sections F3 through F5, which addressed more general I sections previously, and consolidate those three sections into one section F3 that has a number of improvements in it. So I'd like to kind of show you how the new provisions are working, and I'll relate what I show you here back to what's in the current standard. So the way the new section F3 sets up is when we're looking at calculating flexural resistance, we consider three limit states. Number one, yielding and web local buckling. So we're going to look at that first. And that essentially sets a plateau resistance for the section. So this is similar in Eurocode, where if you have a class 1 or a class 2, you have a plateau, right? And the resistance is the plastic moment. If you have a class 3 section, then the resistance is reduced. I think we have a little more detailed approaches there, essentially a linear transition between plastic moment and yield moment in that range. And if we have a slender web, well, that would essentially be a member with a class 4 web, and we have a reduction factor that approximates what we'd get in Eurocode or in the Indian standard by applying an effective width reduction to the web. Once we have that, then we'll look at how we use that with checking flange local buckling and lateral torsional buckling. So the first bullet here is pretty much what I just said. The plateau is defined here by the yielding and web local buckling limit. And in large part, the provisions are equivalent to the AISC 36022, the current specification in sections F4 and F5, but everything's consolidated and there's some improvements here in the calculations. If you dig into the sections F4 and F5 at present, you see some reduction factors called RPC and RPT. Those have disappeared. But the expressions are still the same, they're just written more directly without those factors. And there still is what's called a bin buckling strength reduction factor if you have a slender web. That was called RPG in the current specifications, and we've modified that to RB for bin buckling in this specification. So the way the calculation of that plateau strength works, and if you've got a compact web, so in AISC, a compact web, and I'm going to refer to Eurocode a lot, knowing that the Indian standard is largely very close to Eurocode. So I'll mostly just make comments back to Eurocode here. If we have a compact web is basically class 2 in Eurocode. So we're looking to be able to develop the plastic moment resistance. There are other limits that would be equivalent to Class 1, but the main specification provisions are just focused on calculating strength. So the plateau strength is referred to as M subscript W, and it's equal to MP. If you have a compact web, if the web is non-compact, then there's simply a linear transition between MP and MY, between essentially a Class 2 limit for the web and essentially a Class 3 limit for the web. So Class 3 is what in AISC we would call a slender web. And then when it's a slender web, the strength is less than the yield moment, but rather than work directly with an effective width calculation in the web, we have a rather ancient equation that was developed way back in the day by Professor Bosler in the early 1960s. And that equation is the RB equation, was denoted RPG in the previous, in the current AISC 22 standard. So a fairly significant change here is with singly symmetric sections that have a larger flange in compression. So if you have a large flange in compression, your neutral axis of the section it moves closer to the large flange, right? If the section is doubly symmetric, or if it's singly symmetric with the smaller flange in compression, then we calculate a yield moment, or a yield moment to the compression flange, and that's simply the yield stress times the elastic modulus, the elastic section modulus, and the term that's the general term HCY here is basically the web depth and compression at yield is equal to the elastic depth of web and compression. So with these sorts of sections, if it's singly symmetric, the tension flange has a smaller stress when we're reaching the yield moment, and the compression flange has a calculated stress of it's just reaching to FY. If it's a section with a larger flange in compression, then we've implemented a mechanistic calculation of yield moment when the compression flange first nominally yields. And so for this type of section, we're going to get first yielding at the tension flange, then we have a spread of yielding up the web as we continue to increase the moment. And so once we reach nominal yielding of the compression flange, you're going to have a stress distribution like you see here to the right. And HCY in this case is basically, or HCY over 2 is the depth from the bottom of that compression flange to the neutral axis for this particular stress distribution. Now, conceptually, this is rather clean. However, performing the calculation, if you're going to sit down with your pencil and do it takes a bit of thought. It's possible with homogeneous cross sections, or all plates the same yield, that we can we're able to derive a reasonably succinct formula that's going to be provided in the commentary for this. Here's an equation that you can use to calculate the yield moment to the compression flange. Now this gets us a lot of advantages. One, I don't know how many times Dr. Lakshmi Priya complained to me about how conservative the existing tension flange yield provisions were in the AISC specifications, particularly if we have a slender web. And those were frankly a kludge, basically to stay away from trouble, because before, where in Eurocode, now I would think it may be the same in the Indian code. If you have a singly symmetric section, you calculate the yield moment as the smallest moment at which you reach first yield at either flange. What the American codes did is we say, okay, well, we're just going to get a yield moment to either flange, and if you have this case of a larger flange in compression, we ignore the fact that we've yielded a large portion of the section in tension, and so you can get a yield moment that's actually larger than the plastic moment because you ignored tension. It's kind of a silly calculation. So we've cleaned that up, and we no longer need this tension flange yielding limit state to try to stay away from trouble where the equations are not valid. We calculate the yield moment mechanistically for this case. And just like if you had a composite section, so you have a composite slab in positive bending, and so you've got effectively a large compression flange at the top, right? When we design composite girders, we allow say extensive yielding through the web in calculating their strength. Usually we'll count on the plastic moment, and so this is essentially paralleling that. Your MYC here, it's a moment at first yield that we use as a base for continuing the calculations, but it's the MYC in many sections that behave this way is very close to plastic moment. Now, along with that, there is an equation that is currently case 16 in the AISC table B41B. That is a more general equation for a plastic a compact web limit. The equation, if you compare it to the equations in Eurocode for class 2 web, is a fairly reasonable approximation of what you get with the Eurocode equations, but it's a little more succinct. The compact web limit is a function of the ratio of plastic moment to yield moment here. For doubly symmetric sections, then that ratio of HCY to HP becomes 1, and so the equation simplifies. But if you have sections with a relatively large MP to MY, you tend to get lower or a lower limit for your plastic or compact web limit here using this equation. And the non-compact limit, Dr. Lakshmi Priya basically discovered this in her research, that there was sensitivity in terms of what we should use for that limit to the ratio of the compression area and compression in the web to the area of the compression flange. Now, the non-compact limit of the web limit is basically what we need for the web to be able to get to the yield moment of the cross section. And so, based on Dr. Priya's work, we've got if you have a section that has a relatively large web compared to the flanges, so often if you have a very deep section with narrow flanges, you're going to tend to have a CRW that's 4.6, which is more conservative than what we have used in the past, which is the upper limit of 5.7. And then this is the equation that is an approximation of basically the influence of using an effective width if we were to take that approach in the web. And the equation is the same as the RPG equation that we've been using. However, we're using it with terms. The A sub W, the lambda W, and the lambda RW are keyed to the HCY, the depth of web and compression for the general case, whatever you have at the first yield of the compression flange. All right, so that's the plateau strength. And then given the plateau strength, you'll see in the next few plots, we're plotting either flange local buckling strength or then lateral torsional buckling strength on the ordinate, and then versus slenderness term on the abscissa. So here the slenderness is of the flange, BF over 2TF is lambda F. And the flange local buckling rules have been liberalized a bit. You can gain some significant advantages in this case if you have non-compact or slender flanges in compression. So the new calculation will basically just use this linear function, which is a coarse representation of what we would get if we included the if we basically did an effective width approach to calculate the contribution of the compression flange. So it's accounting for some post-buckling strength, but tends to be accurate in some cases, but often still conservative. But it's a more it gives you a larger strength than what we've been using, where the dash curve here is the AISC specifications previously have just been using a pseudo inelastic buckling or elastic buckling calculation for the compression flange. For the lateral torsional buckling, there's some fairly significant changes. For the lateral torsional buckling, we're moving in the direction of using a non-dimensional slenderness that would be square root of Fy over F critical. And so if the non-dimensional slenderness is less than the limit lambda p LT, so we'll look at how we can write that here in a minute, where we reach the plateau strength. Otherwise, there's a linear transition, and then when we reach the limit lambda r LT, then basically we're into an elastic buckling calculation. So we still work directly with an elastic buckling LTB resistance in that region, in the last region here. So I'll come back to this curve and show a little more about it in a minute. That inelastic to elastic lateral torsional buckling transition, that's tied to the slenderness lambda RLT, and it's tied to the moment ML. And so ML is simply the elastic lateral torsional buckling moment at this particular LTB slenderness. And in the general provisions, we're using 50% of the yield moment as the moment at that transition. If it's a rolled I-section member, we're using 70% of yield moment. So that's consistent with the earlier sections of Chapter F. Those sections, the first section and the second section F2 are addressing only compact rolled sections. So general sections here, if you have a rolled section, using ML equals 0.7 MYC gives you comparable results to what you would get from section F2. And the LTB slenderness at the elastic to inelastic transition, lambda RLT, that's simply square root of Fy to basically ML's the elastic buckling moment at that level, so ML over SXC. Now, it's often questioned in the U.S. that a lot of concerns we're essentially lowering that limit from what we've used traditionally, 0.7 to 0.5 of the yield moment. So a lot of engineers will ask the question, look, your residual stresses, are they really that large where you need to reduce to only 50% of the yield moment? And so the answer to that question is there's a lot more going on than just a moment, a stress due to the major axis bending plus an initial residual stress. So we're a little past the peak load here, but at the peak load in this test, you can see there's quite a large amount of lateral bending of that compression flange on the top. And so we've got a behavior where there are initial residual stresses, then to that we're adding our major axis bending stresses, but with any out of straightness of the compression flange, as you're approaching the elastic buckling moment level for a member that has a slenderness close to lambda RLT, you're getting substantial lateral bending, and that's tending to cause a reduction. That's a big part of what's causing the reduction in the strength. So what you can see here on the right is basically our prior prediction for this particular test, and then the test result. Now that was the test I was showing you there was a moment gradient test of a slender web. And so that's the simplest case. In those cases, the lambda PLT is a constant 0.35 for all cases. However, what we were finding was that if you had a web that was more typical of a rolled section, well within the compact web limit, the provisions in section F2 are actually doing a good job of predicting the experimental results, whereas the approach that we were looking at that worked well for slender web members wasn't working so well. It was tending to be quite conservative. And the way that we looked to try to solve that was basically to adopt essentially the way that it's being done if we have a very stocky web. And so I'll try to show this on the next slide to explain it. But the lambda PLT prime equation here is basically what we get with the current approach in section F2 of the specification, but except we put a cap of 0.8 as an upper limit on it. And so if you have a web that's less than 70% of the compact web limit for its slenderness, we use lambda PLT as lambda PLT prime, and you can see that's a function of the moment gradient, C sub B. So we use our moment gradient design expressions for C sub B and get an increase in the plateau length with doing that. Intermediate cases is a simple interpolation between the lambda PLT equals lambda PLT prime for a compact, a highly compact web, and the lambda PLT equals 0.35 for a slender web. So this slide is an attempt to show how the current section F2 works and the way that AISC has traditionally applied the moment gradient factor CB. CB is a constant that is basically calculated as the ratio of the elastic lateral torsional buckling strength given whatever variation in moment or moment gradient that you have within the unbraced length you're looking at, divided by what would be the elastic lateral torsional buckling strength if we just had uniform bending within the length. And so AISC since 1986 has always taken that elastically calculated CB, and then we scale the entire uniform bending strength curve by that factor, but then we limit the maximum to the plateau strength. So here I'm showing it for a compact web section, so the plateau strength would be MP, and if you have a high enough moment gradient, you can actually create a situation where the calculated strength is an elastic lateral torsional buckling strength. All right, there we go. That's this part of the curve here, all the way up to MP, because the uniform bending strength curve is plateau, and then the dashed curve, the dashed gray curve that you see here. And so if we scale by CB, and if CB is large enough, we end up with basically an elastic curve and then plastic moment strength. And I'm showing this as a case of, well, how confident are we that we can actually get that? And so we've done some work that's went back, where we've gone back and we've explored the available experimental test data in the literature for, okay, what is there justification for this? And what we can see is that this approach, where again you're using an elastic CB factor and just scaling it up and essentially ignoring any extra plasticity you get, except you cap it off at MP, that's working fairly well for rolled sections up to a point. And there's some additional data than this, but this is an experimental test from Du and Kittapornchai in Australia, where they were pushing the limits here with a 3-point bending test. So C sub B is 1.74 by the AISC equations here. And you can see that you can make an argument where, well, is the current spec bad here? Or doesn't look like it's missing it by much. Is this just showing one data point here that's low? The new provisions that I just tried to explain to you are the dashed orangish curve there. So you can see those are fitting that data reasonably well. And if I were to show you some other plots where we've looked at comprehensively at all the tests we can access, you can see there a tendency where the prediction tends to be a bit low as we're approaching this limit, where the elastic buckling curve would tend to be coming in close to lambda r, L2. A problem, I'd love to do some more experimental tests to gather further data on this. There really aren't any super long rolled section tests to look at the limit of this if you really push it. So this is a beam type section here that they're testing. It's 3-point bending. CB is 1.74. If you had a case with reverse curvature bending, what I see from FEA is that, yeah, it's really getting suspect. So we're suggesting that we should put a cap there on the way that we use section F2 to not allow this very simplistic scaling. It works well up to a point there, but I think once we're getting to higher slenderness values, it doesn't work so well. One thing that kind of saves us here is for a rolled section, the section properties, the flanges are typically wide enough, even for the beam sections. You'd have to have a super long beam to create this problem, and you're getting into a realm where you'd be challenged that you're not going to have a serviceability problem if you were using such a beam for the lateral torsional buckling strength. These are rolled beam sections, so the web's really not stressed very much in terms of shear stress. Yeah, it's really a issue of the way we scale by CB. Dr. Helwig and his associates at University of Texas, Austin, have been doing parallel research where they had some concerns about the influence of web shear on the elastic LTB resistance and the web shear tending to cause lateral distortion of the cross section. I'm just going to kind of give you a light touch here on these equations and essentially show you the results that we get. So with their equations, one thing that we've done in the past, if you have a slender web section, is we would base the strength on J equals 0 in the American standard. I think we're the only ones in the world that do it. And the part of the rationale for that was that gives some approximation of lateral distortional buckling effects. You're basically discounting the help from St. Venant torsion. It also simplifies the equations significantly. If you're doing a hand calculation, it creates a major pain in the neck for Balint if he's going to try to implement that, because when's Consteel going to use J equals 0 and when is it going to use a J for different calculations? So I think it's a good thing that we're moving in this direction, and we'll always calculate the LTB resistance using all the terms from the mechanics for the elastic buckling resistance. But for these cases where there's a clear reduction in the elastic LTB strength due to elastic lateral torsional buckling, we're taking a reduction due to the shear in the web. So this shows results for essentially a metal building type girder section. So it has 6 by 3/8 inch flanges and a 36 by 5/16 inch deep web. And what you can see here is that the test simulations, I'm just showing you simulation results here. If we're at an unbraced length here, so this is basically forked boundary conditions at the end, or torsionally simply supported, or K equals 1 for lateral torsional buckling if you're calculating an effective length factor for lateral torsional buckling. And so if we have a length for this specimen, an unbraced length, that is in the neighborhood of about 10 feet, notice what we're getting is that where the current standard would predict you're getting about 85% of the plastic moment here, we're only getting about 60% from the simulation. So these sort of simulations were things we did early on, working off of the concerns that were voiced by Professor Joe Ura with some of the things with the distortional buckling, with the elastic buckling studies. And what we were finding is actually these sections, the results are even more suspect for the current spec calculations. If we're in this range where we're starting to scale the elastic buckling resistance above a level where we would anticipate some onset of yielding in the section. And you can see the black curve there. That's the new Section F3 provisions for this particular case. I'll show some curves that summarize this with various test results in a minute. These are some of the photos from the test that relates to that what I just showed you with the simulations. And if you look at the test in the the photo in the upper left, and look at the grid pattern on the web or the speckle pattern further along the web there, you can see that definite distortion of the web in an S shape. So that's what's causing us trouble in terms of getting to the moment resistance. It's basically that lateral distortional buckling, and it's exacerbated by the onset of yielding that's happening in the section. And if you do FEA simulations and plot, this is a plot of results that you get looking at the strength limit on this particular section or specimen. The moment diagram is essentially triangular, 0 at the supports and maximum at the center span. But notice that we're getting a lot of yielding that's out within the unbraced length. So why is that? You say, shouldn't I get the most yielding where I have the largest major axis bending moment? Well, no, and that's what's happening is that significant lateral bending of the flanges that I showed you in the experiment in the video a bit back. So that lateral bending is causing a situation that gives early yielding of the compression flange out within the unbraced length. And that behavior is exacerbated by the web distortion that we're getting and that's pushed by the high shear stress in the web. So given some FEA simulations to try to get our handle on the problem, we designed a suite of 6 experimental tests to try to get confirmation of the behavior. And so we did test with 3 three-point bending tests, and we had 3 tests where the test configuration was to put the critical unbraced length in full reverse curvature bending. And for each of those tests, we had specimens with a range of H over TW. These are doubly symmetric sections here, so H over TW is the same as HC is HCY is HP. And so the Stockier web had an H over TW of 77, so that would classify it as being close to compact, but it's slightly very slightly non-compact using the provisions that are moving forward. Then the other 2 webs had an intermediate slenderness of 115 and then a fairly high slenderness of 192. And I want to highlight what's going on with the case with the intermediate web slenderness. I'll use that one to kind of highlight for you what's going on. And then showing versus simulation results, then I'll show you the experimental results in a minute. So if we look at what's going on here, the plots in this case are actually done using J equals 0, using an RB equal to RPG, less than 1, and so this is basically the approach that Balint has implemented in Consteel. It's slender web, so the calculation is basically the same calculation, or nearly the same calculation as what's in Design Guide 25 for designing frames using non-prismatic members. What we can see here is that there's, again, fairly substantial overprediction. And so the top plot here is for a 3-point bending test with this intermediate slenderness web. The bottom plot is for the reverse curvature bending. And so with the higher moment gradient, with the reverse curvature bending, we've got even more damning results in terms of the predictions from the current specification, which is the top curve here, and then the shaded region showing the comparison to that. And what we're seeing from analysis of tests and of the FEA simulations is this inability to predict the strength here in the current standard. It's coming from web distortion effects, and that also being exacerbated by the way that in the current standards we scale the uniform bending strength by CB without considering, okay, are we getting any impact of the additional yielding that will occur before we reach the plateau strength. And so finally, this plot, or this slide shows experimental results and FEA simulation results for the suite of 6 tests that we studied in our work. So across the top, these are all 3-point bending tests. Across the bottom are all the reverse curvature bending tests. So higher moment gradient in the bottom, higher shear. And as we go from left to right, the plots on the far left are all with the stockiest web. And so here the H over T being reported is the H over T based on the measured dimensions. The middle is the intermediate web slenderness. The plots to the far right are the specimens that had quite high web slenderness. So what you can see throughout these, again, the middle and the rightmost plots, those are specimens all that classify as slender webs in the current in the standards that is proposed for 2027. And in all those cases, there is the one here in the middle on the top. Our FEA simulations here in these plots were done with the imperfections that we measured in the lab before doing the tests. And for this specimen, it seems that, well, if we used what we would typically do in terms of analytical imperfections that were based off of using a buckling mode for lateral torsional buckling, flange local buckling, and web local buckling, and combining modes, we get a very close prediction from the test by the FEA simulations. The FEA simulations are the open squares, and the tests are the red circular. Those test results are the red circular symbols. With that exception, I think we're reasonably pleased that the FEA simulations and the experimental results are very close and are showing that, yeah, we've got a significant problem here that gets worse and worse the higher the moment gradient we have. Now the plots on the far left, for these, the dashed blue curve is basically what we would have if we just used the constant lambda PLT of 0.35. That's what we actually did in the, that's the way it's done in the Design Guide 25. However, with the increase in lambda PLT that I showed you earlier, that gives us the black curve. So we're basically, for these stockier webs, increasing that plateau length to get a better prediction. And so you can see here where we are relative to what we obtained from the simulation and from the experiments. This just shows another plot with the full simulations, FEA simulations of the various lengths with these specimens and where the simulations fit more broadly. Now, the gold curve here in these plots is what we get from second generation Eurocode 3, which is a little enhanced relative to the Indian code, a little larger strength. The Eurocode curves, you can see, are tending to predict things rather well for the most slender webs, but that are tending to predict a little more conservatively as we get stockier webs. And our best take on what's going on here is, so these curves, using the Eurocode 3, we're basically required to use curve D of the LTB curve, which is the most damning it gives you the lowest predictions in strength. And so our thinking is that curve D is probably a little more conservative than is justified for these types of cases. If we were to use curve C, we'd be very much closer in terms of correlation with what we're getting with our test simulations and with our experiments. And this shows the same plots, but plotting in terms of the normalized slenderness lambda LT. So those were all doubly symmetric specimens. We also did a suite of tests where we looked at singly symmetric sections with larger flanges in compression. And so in these cases, the web is quite thin. You can see, if you look at the speckle pattern or the grid pattern on the web here, you can see that there's a significant S shape occurring in the web as we're reaching strength condition. However, for these specimens, the neutral axis, either elastically or as we start developing some yielding, is very high and is very close to the top flange here. And so the web is in predominant flexural tension, and as a result, based on our calculations, this section actually classifies as a compact web. And so we're using plastic moment resistance as the plateau strength, and you can see where this is coming in here. So the top plot in terms of is the strength normalized by MP versus an effective length. The bottom plot is the same ordinate versus the non-dimensional slenderness lambda LT. The other thing with these tests, because of the thinness of the web, we're actually using quite substantial post-buckling strength of the web and shear. And so these curves that in the plots that go upward from left to right, those are calculated shear strengths. The green curve on the bottom is the theoretical shear buckling strength of the web. So you can say we go well past that. The dot dash goldish looking curve, that's the tension field shear resistance of the web. And you can see that as we reach lengths of this specimen where it's becoming rather short, but it's a 3-point bending test, and we're starting to reach a condition where we would fail it as a shear test. The shear provisions you can see give us a conservative limit on those tests. So this gold curve here versus what we're getting from the simulation results in the curve with the black dots. And same type of behavior I showed you earlier for a specimen where we're reaching elastic buckling resistance at a point that in the current AISC specification would be essentially taken as the plateau strength. We see substantial onset of yielding shown by the blue areas here out within the unbraced length as we're approaching that condition, approaching the ultimate strength here. And in this case also, because of the large compression flange on the top, we're getting early yielding in tension in the peak moment region. So all the large amounts of blue there in the bottom of the specimen is showing that the amount of where the yielding has progressed basically at this maximum strength here of the specimen. All right, so that's an overview of where the American provisions are going. I've on the general tab on the Google Drive. The provisions are provided there. There's also the current AISC 36022 specification and commentary there. And then one other file there that is the table B in Chapter B that addresses the compact and non-compact web limits for members in Flexure. So we've been looking at this quite intently for a number of years now with the AISC specification committee, because clearly there's a safety issue, or at least an issue that we're not doing, the specification isn't doing very well if we're getting situations where the predicted strength is like close to 1.0 and we're only getting more like 60% of that. We believe that the provisions that are moving forward solve the problem for slender web I-section members. We use the elastic CB only with calculating elastic lateral torsional buckling stress. We're not scaling a curve that's an inelastic strength curve by an elastic factor, elastically derived factor. We're expressing the LTB strength curve in terms of the non-dimensional slenderness, lambda LT equal to square root of Fy over Fe LTB or F critical LTB. And that's similar to the way we handle column curves. That's our argument, is that, look, we do this for columns, why shouldn't we be doing it for beams? And we're avoiding applying that C sub B in ways that or in cases where we can see that it's not performing well. We've used this approach in Design Guide 25 since its first edition in 2011, so it's not that it's new to North American practice. And but the problem that we tried to address in the work I showed you here is the Design Guide 25 tends to provide conservative results when we have stockier I-section webs. So we've addressed that by implementing equations that achieve the same calculation that the current AISC approach achieves, in the limit that the web is less than 70% of the compact web limit, and then with an interpolation between those those results and the results for slender web for intermediate web cases. And then we have a reduction factor on the elastic LTB resistance for accounting for shear stress in the web. And so that's, I think, a good change there in terms of we can base our calculations all uniformly on the mechanics with using all the terms, both the St. Venant torsion contribution as well as the warping rigidity contribution to the lateral torsional buckling strength. In all cases, then we take a reduction off of that. I think it's fair to say that the Eurocode was results are giving adequate predictions until we get, I think generally they tend to be conservative to accurate, and the Eurocode is not using a shear reduction factor. But the American code tends to, we tend to base our elastic LTB resistance on a theoretical elastic buckling. So I think we're a bit more on edge there with the way we do the calculation. And so I think it's with good reason then that, okay, if we're going to base our elastic buckling resistance calculations that way, we should probably be taking this reduction due to lateral distortional buckling. And there's a number of references here that if you're interested in following and maybe possibly even taking some of this work further in your studies and your work, you can dig into what we've been studying. All right, so that's the lecture for the day.